All right, we're getting into chapter 19, which is on carboxylic acids and essentially the OH bond and its acidic properties. We're only covering 19.1 to 19.11. This chapter mainly talks about structure and properties, and we'll get into more reactions in the next chapter we discuss. You can go ahead and copy most of this down, and we'll go through it. So beginning with structure, if we look at a carboxylic acid, in this case acetic acid, the important parts are the carbonyl and the OH bond. And that carbonyl carbon must be bonded to this oxygen. If we look at the bond lengths, we've got a shorter bond in the double bond, and then a longer bond for the carbon-oxygen single bond. And that should make sense. The bond angle here is what we would expect for an sp2 situation. It's barely smaller than the predicted 120 degrees. So everything makes sense and is what we would predict about the structure. We know that this is a very polar bond, that carbonyl. So the carbonyl oxygen, just like any other carbonyl compound, is partially negative. Carbonyl carbon is partially positive. For physical properties, due to that dipole and the fact that these are strong hydrogen bonders, being acidic makes this a stronger hydrogen bond than an alcohol would have, because it's a better donor of that H+. Because of the strong hydrogen bonding, usually carboxylic acids exist as dimers. And so a carboxylic acid can line up in a very favorable, stable conformation with another carboxylic acid, and form hydrogen bonds. Which I've labeled in red. So this tight structure is very stable. Because of that dimerization and the strong hydrogen bonding in general, carboxylic acids have typically very high melting points and boiling points, higher than alcohols. And because they can hydrogen bond so effectively, they tend to be water soluble unless there's a large alkyl or carbon group bonded to them. Here are some examples of some compounds to kind of go through the whole progression from the beginning of the class with some actual data. We want to compare structures that have the same molecular weight for boiling point, so approximately same surface area. So if we look at molecular weights, these are all effectively the same, so about the same surface area that we would be looking at. And now we're going to compare their boiling points. Well, butane has a boiling point of 0 degrees. Which is what we would expect for only van der Waals or dispersion forces. With a polar carbonyl, that increases the boiling point significantly, up to 48 degrees Celsius. With an alcohol, again, a giant jump now that it can hydrogen bond donate to 97 degrees for propanol. But with a carboxylic acid, again, another huge jump up to 118 degrees. So carboxylic acids, extremely high boiling points. What you'll need to know is how to prepare carboxylic acids, and we've already learned 5 different ways. What you should do in your notes is leave a space and create an example for each of these ways. Some of these we have recently discussed, and some are a little bit older. But so, for example, we can prepare carboxylic acids easily from primary alcohols, and you should know that reaction. That involves chromic acid oxidation. From aldehydes, again, this is chromic acid oxidation. from alkyl aromatics. So for example, like toluene or ethylbenzene can be used to make benzoic acid in a reaction. Grignard reagents can make carboxylic acids, and we know that reaction as well with CO2. And lastly, probably least useful, but carboxylic acids can be made from alkynes using ozone to cleave the carbon-carbon triple bond. And if this is done in water, you end up with a carboxylic acid or two carboxylic acids, potentially. Carboxylic acids are acidic because the anion that's formed once they donate H+ is resonance stabilized. And this is something we went over in the first semester in the chapter on acids and bases. Resonance stabilization is a huge stabilizing force for anions and cations. If we look at this structure, we can draw a resonance hybrid. Looks like this, where you would have a partial negative charge on each of the oxygens. And so each of those oxygens are identical once the acid is deprotonated. For the carboxylic acid, either one of these bonds can actually be determined in terms of its bond length, and it's 127 picometers. And so that's right in between a single and a double bond, carbon-oxygen bond. So it is effectively about a bond order of 1.5. So stronger than a single bond, weaker than a double bond, and that makes sense from the resonance hybrid. Acetic acid is your typical carboxylic acid. Normal carboxylic acids have a pKa of close to 5, a little more acidic, a very acidic organic functional group. And aromatic carboxylic acids are in the same ballpark. A little more acidic is benzoic acid at 4.2. And so we'll kind of use these for a normal alkyl carboxylic acid as kind of a base. And then well, let's not use the word base, but it's kind of a starting point for acidity. And if it's an aromatic carboxylic acid, we can use benzoic acid as a starting point for comparisons on substituent effects. Because of these acidities, they are so easily deprotonated, almost anything that acts as a base can deprotonate a carboxylic acid. So things even as weak as sodium bicarbonate are typical bases for deprotonation, but you can use sodium hydride, a very strong base, and it will deprotonate, of course, as well. Let's compare these following structures. Each of these has an OH bond, but we have drastically different pKa values. Carboxylic acid, close to 5, very acidic. Here's phenol. Notice phenol is an alcohol, but it's an aromatic alcohol, and its pKa is 10. We can compare that to a normal alkyl alcohol with a pKa of 16. And then think about why we have a pKa of 10 here. And let's compare phenol to both of these other functional groups. Well, whenever you're thinking about acids, you have to deprotonate them and look at the stability of the resulting anion, because that really tells you everything you need to know. And so if phenol is deprotonated, O- is directly bonded to the benzene ring. And so you can draw many resonance structures that distribute this negative charge to other atoms in the ring. Of course, those are going to be carbon atoms, which are not that electronegative, but you can draw many different resonance structures. Try and draw some and compare those to the ones found in the textbook to see if you've got them all. If we think about the resonance or the anion here, in the case of the carboxylate, you can draw resonance structures that distribute the charge between two oxygens. So even though there's less resonance structures, the fact that the charge is distributed to electronegative oxygens makes this more stable as an anion than the phenoxide anion. If we compare this then to the ethoxide, well, that negative charge is confined completely to the oxygen. And so we have a much higher pKa value. Remember, the difference here is basically each unit is a factor of 10 difference. So this is about 1,000,000 times stronger of an acid than ethanol. And then we have almost another jump, about 100,000 times more strong of an acid with the acetic acid. This is good to recall the inductive effect. So if you remember from earlier chapters when we discussed acids and bases, the inductive effect was an important factor for determining pKa's or rationalizing pKa's for different structures. So when we put an electronegative chlorine atom, think about what that effect should be on the pKa here. So you think about the resulting anion. What if there's a chlorine here? Will that help stabilize the structure, or will it destabilize the structure? Well, here's our pKa values. And again, you don't need to memorize these values, but you should be able to explain approximately why they are the value they are. And it makes sense. If we have an electronegative chlorine, well, that creates a dipole along the carbon-chlorine bond. So it pulls electron density its way. And so that's going to create another induced dipole pulling electron density from this carbon. And so in the anion, when you have an electronegative group out here, all the negative charge that's confined to these two atoms in the resonance structure will kind of be slightly smeared across the bonds. Those sigma or pi bonding networks, but basically the sigma bonding network will kind of help draw a little bit of that electron density away. And so it's a way of spreading out the electron density. And so we can see that, in that effect in one chlorine. The more chlorines you have, the stronger that induced dipole is going to be drawing electron density this way. And so that explains why we get a significant effect with one chlorine, but then each chlorine you add here is another significant effect. So much so that it drops below 1 for trichloroacetic acid. What would we predict then for fluoroacetic acid? Think of a value based on the data you have here and what you know about fluorine. And then what would you predict for 3-chloropropanoic acid, comparing perhaps to this one as well? Well, fluoroacetic acid has a pKa of 2.6, so slightly lower, which means it's slightly stronger of an acid. The dipole here is going to be stronger than the dipole here because fluorine is more electronegative, so that'll make a slightly stronger inductive effect. Here, the dipole will be about the same in this bond as this dipole, but since it's farther away from where the extra electron density is going to be, it'll be a weaker effect. Very much weaker. So I want to provide a couple more examples and think about a way to rank them. So let's look at these and think about what we would have for pKa values. And you can just guess at a number or put one in your head. We know the pKa for this. And so this is where the numbers fall. When we have an electronegative oxygen here, similar to chlorine, not quite as strong of an effect, but a significant drop in pKa due to that dipole. This is an amino acid where the amine group has been protonated. And so when you have a positive charge, there's a very strong dipole associated with this bond. And so that's going to be a very significant inductive effect, more so than if it was just a neutral nitrogen, because that positive charge is really going to want electron density around it. And so these values should make sense. What I would like you to consider for our next class is now some aromatics, and you're going to make use of what we know about electron donating substituents and electron withdrawing substituents. Okay, so benzoic acid has a value of 4.2. And I'm going to label these two examples. You might think about what you would expect for those two. And then I want you to rank the following 4 examples as best you can compared to this series above, thinking about the electron donating or withdrawing nature of the substituent. When we have a rich electron donor here, our pKa value actually increases. Does that make sense? Think about the anion and its stability. If we have a strong electron withdrawing group, the pKa should decrease, and in fact it does. So think about where these pKa's might lie for all of these groups and try and rank them. And we'll go over that next time.